So the first thing we're going to look at is where we find these metals. So which group, so that's in the heading obviously, we find them in group 2, but they also have another name, the alkali earth metals. So they're found in group 2 of the periodic table. I'm just going to move this down, okay. And they readily form X2 plus ions, so they readily lose 2 electrons when they react. So this is an oxidation reaction. So again, a bit of recap if you like. It's an oxidation. So metals generally and readily oxidize rather than reduce, so they will always lose electrons. It's a good kind of thing to remember for future reference. But also the reactivity of group 2's metals increases as we go down the group, similar to group 1, and for exactly the same reason. So when we look at ionization energies, we are going to look at for group 2, we'll just consider this point here on the right hand side. The next thing we're going to look at is the structure of atomic radii versus ionic radii, and we need to know how they change as we go down the group. So down the group, both of these increase, and they both increase for the same reason. They just have more energy levels prior, or more energy levels than the previous, I should say, group 2 metal, i.e. there's more energy levels, they're further away from the nucleus, therefore there's less attraction on those outer electrons, so as you go down the group they get bigger. However, if we increase the number of shells or energy levels, obviously it increases. But if I'm going to compare metal atoms to metal ions, there is going to be a significant difference between the two. When we form a metal ion, especially in group 2, they'll always lose those 2 outer electrons, and therefore will lose an energy level. And as a result of losing an energy level, it will be smaller than the respective atomic radii. So however, the X2 plus, so this is what I've written here, ion will always be smaller than the respective atom or atomic radii due to the reduction in shielding. So there's less or fewer energy levels. So I've got this diagram here to help me illustrate that. So this one in blue is the atomic radii. I've got all its electrons, including its 2 outer electrons. You remove 2 electrons from it, it's going to get smaller because you've lost the outer energy level. It's definitely smaller. Not only that, it's worth considering at this point that you have more protons than electrons, so you have 2 more protons than electrons. Let's call it the proton-electron ratio, and therefore there is a greater nuclear attraction on those outer electrons, which are closer, and they get even closer to the nucleus, and therefore there's a reduction in the ionic radii. So the next thing we're going to need to look at, which kind of links onto this, is the ionization energies. So ionization energies, we're going to first look at successive ionization energies, and then look at the first ionization energies of each of the group 2 metals as we go down the group. So first of all, successive. So we need to know whether these increase or decrease for a particular group 2 metal. It might be worth pausing the video at this point and seeing if you can tell me whether they increase or decrease and justify your answer, so explain why. So good time to pause the video. So hopefully you've had time to write an answer down. We should know that they increase. Successive ionization energies always increase. But why? And the reason's always the same. The reason is that as you remove more and more electrons, let's hide that for now. As you remove more and more electrons, you end up getting a higher proton to electron ratio, so just more protons to electrons. And as a result, there is greater nuclear attraction. That does not mean that the nuclear charge has increased. It doesn't increase. It's exactly the same as before. It's just the attraction on the outer electrons is greater because you have more protons compared to electrons. And as a result, the electrons are pulled in that little bit tighter, closer to the nucleus, and as a result from that, it takes more energy to remove an electron. So every time you remove an additional electron, this gets greater and greater. So this kind of attraction on the outer electrons gets greater because there are more protons to electrons. So that's successive ionization energies. The next one we're going to look at is the first ionization energies. So another good time to pause the video, try and tell me what you think happens to first ionization energies as we go down group 2 metals, and try and justify your answer. So again, worth pausing the video at this point. So hopefully you've had some time to write something down in regards to this. We should know from previous topics, periodicity, is that they decrease. The explanation of why is, again, the same as group 1. The increase in energy levels increases the shielding, and this obviously goes for other groups as well, I should mention. The outer electrons, as a result, are further away from the nucleus. Every time you go down a group, every time you go down a period, I should say, you increase the number of energy levels. That's an increase in shielding. The outer electrons are further away from the nucleus, and as a result of that increased distance, the weaker nuclear attraction on the outer electrons, so therefore it takes less energy to remove an electron. It's also a good opportunity to see if you can write the definition of the first ionization energy, which will pop up on the right. So again, you can pause the video and see what you get. So you should have got essentially this definition. So the energy required to remove 1 electron from 1 mole of gaseous atoms to produce 1 mole of gaseous plus 1 ions, and we've got an equation to also back up that definition, or another way of defining the first ionization energy. To be fair, you've got to make sure that 1 mole appears at least once within that definition. I try and put it in before the gaseous atoms part and the gaseous ions part as well, just to make sure we're covered. Right, the next thing we're going to look at are the reactions of group 2 metals. Now, I've used X as a generic symbol to represent a group 2 atom and ion in relevant places. The first thing we're going to look at is its reaction with oxygen. So you'll see what I mean here is I've used X. Now, so the balancing is important. Make sure you've got it balanced. All you need to then do is replace the X with a relevant metal, whatever that might be. Okay, and in this case we get a metal oxides, and remember, metal oxides are bases. Water is the next one, and I've got 2 equations here. One's for steam, hence the state symbol gaseous, and one's with liquid water, hence the state symbol L. The products slightly differ though. If you react with liquid water, you get the hydroxide. However, if you react with steam, you get the oxide. Both are bases, but obviously hydroxide, if it's soluble, it's an alkali. So alkalis are soluble bases, remember that. But they both produce hydrogen gas in each case. The next one we're going to look at is chlorine. Pretty straightforward. Metal plus chlorine gives us a metal chloride. And again, it's worth keeping that in mind. It's very simple. Just make sure you got the balancing right. It's 2 Cl minuses for every X2 plus ion. So make sure you got the formula right. It's where, again, students slip up. Right, we're going to move on to reactions of group 2 compounds. Right, so the compounds that we're going to look at are metal oxides and metal hydroxides. We're going to look at metal oxide reactions with water and relevant acids, and hydroxides with acids only. And these reactions you do need to know, but again, I use X as a generic kind of symbol for a group 2 metal. Just keep that in mind. So let's have a look at oxides first. So we've got here metal oxide plus water, and we get the relevant hydroxide. Always check if it's balanced too. The next we're going to look at are the acids. So I'm just going to pull this down from here, and we've got the acids. Now we've got hydrochloric acid, we've got hydrochloric acid, we've got sulfuric acid, and we've got nitric acid. Just be mindful again of the formula of the salt, or the salts that are being produced, because remember X is 2+, so that would be the formula for a chloride salt, sulfate salt, nitrate salt, because of the respective charges. worth keeping in mind here that the balancing will also change in regards to which acid is being used. So again, make sure that balancing is right. If you struggle on balancing ever, it's always worth checking whether your formulae are correct, because sometimes that can mean an equation is very difficult, or if not impossible, to balance if you've got the formula incorrect. Remember, this is a neutralization reaction, so these are bases and they're reacting with acid, so you get a salt plus water each time. Maybe worth also mentioning at this point, generally nitrate salts are very soluble unless it's lead nitrate, and chloride salts are generally very soluble as well, as long as it's not silver chloride or it's not lead chloride. And sulfate salts, this is something we'll look at later on, but can be soluble, but they change depending on the metal attached to it. Now, the next thing we're going to look at are the hydroxides, the metal hydroxides. So what we've got here are the metal hydroxide, respective metal hydroxides reacting with the relevant acids. And again, this is a neutralization reaction, so these are neutralization reactions. Okay, so all of the bits in blue except for the top one are neutralization reactions, and the ones underneath are neutralization reactions as well. And you get the respective salts again, and you produce water. So not going to spend much time on that. I mean, that's pretty straightforward there, and you can pause the video and have a look at what exactly is happening, but essentially you're still getting the same salt and you're producing water. Right, the final thing we're going to look at is solubility. Now, the solubility is changed for sulfates and hydroxides down group 2. You kind of really want to make sure you have ways of remembering all this information. A lot of this information in group 2 and 7 is just learning by rote. And there's very little understanding involved in comparison to some of the other topics you do in chemistry. It's about learning reactions and how components react with other substances. We are going to look at sulfates. Now, we do know from previous knowledge, I hope, is that barium chloride, barium is a group 2 metal towards the bottom of group 2, is acidified barium chloride is used to detect sulfate ions, and that's because barium sulfate is very insoluble. It produces a white precipitate. Therefore, when you add barium chloride to a sulfate ion, you get this white precipitate coming out, and therefore that means that is not soluble. That should also hint towards the trend in solubility down group 2. We say that the solubility of group 2 sulfates decreases as you go down the group. Okay. And hydroxides, group 2 hydroxides, are the other way around, so they increase as you go down a group. But it's worth remembering about group 1 hydroxides are generally soluble all the way down a group. It's just group 2 they increase and get more soluble, and so therefore at the top they're not very soluble, so we end up having this here.